Okay, hello. Can you hear me better now?
It's much better, much better.
Much better.
It's not, yeah, the sound is gone, the muffled sound is gone.
Much okay. Thank you. Thank you. Thanks for that. Okay. Let's see. Where did we stop now? All right. So I'm sure you guys heard everything else that I said though. Everything from here, but I'm just gonna go, continue from Ethernet fundamentals. So Ethernet has been around for a very long time. Hold on, let me make sure that everything else is good. Okay, everything else is good, I think. All right. Okay, so Ethernet has been around for a very long time, and it's the major mode of network data transmission and transfer at layer 2 of the OSI model. And like I was saying that, you must have seen these cables before. These are Ethernet cables, although these days now what a lot of people use, except if you're working at certain corporations, is Wi-Fi. So you may not necessarily see these cables, but these cables are still predominantly used in server houses. For instance, in the AWS server houses, these are the cables that they use to connect one device, one server to the other, and so on and so forth like that. So it's important to know about them and how they work. So how is data transmission managed through Ethernet connections? All right. So there are some interesting networking concepts to learn about here. And though this area can easily get quite complicated, right? This is a simplified version. Ethernet network access is contention based instead of deterministic. And what does that mean? Deterministic means that the network access should be very, oh, what's going on? Okay. So means that the network access should be very organized and orderly. Okay. But what does this also mean as well? So if a device wants to transmit data on the network, that device had to wait its turn until some sort of electronic token was given to it to signify that it was that device's turn to transmit data over the network. Okay, so to understand this better, let's pretend we're in a classroom together like we are right now, right? So this room consists of you, me, and maybe say let's just say that this room consisted of like 20 or 30 other students. Okay, if everyone started talking at the same time, nobody would be heard or understood. Instead, we'd have a bunch of collisions because everyone is talking on top of each other, right? Now, to solve this problem, we create some sort of a deterministic system to determine who's going to speak at any given time. So if I'm the one teaching in a classroom, I'll say to my students, if you want to talk, you raise your hands. When I call you, then you'll now be able to speak, or you'll be able to say what you wanted to say, right? So this is exactly how deterministic network access systems such as token ring networks work. They do this to solve this issue of collision or traffic within a network. Okay. Now, contention based is different from deterministic. And remember, we said the Ethernet network access is contention based instead of deterministic. Okay, so what is contention based? It is used to determine who gets to access and communicate on the network at any given time. But again, what does this also mean as well in detail, right? So unlike the classroom example, which was very deterministic, and the instructor got to tell everyone who could talk and for how long, the contention based network access model is more like when you go to a local bar or a club with your friends on a Friday night, right? Say you're hanging out with 4 to 5 of your friends and you're all having, drinks, you're all chilling, normally in these situations, people know how to communicate, how to talk to each other in such a way that no one is talking over anyone. There isn't any instructor saying, BC, you start talking for 5 minutes, after which Obi would button. And then Demola, will talk about his new job for 2 minutes before Akim adds to it. There isn't usually anything like that. But this is exactly how the deterministic network access model works. Okay. But in contention based, there's nothing like that. So what actually happens? Um, so what actually happens is that people just talk and commune with each other, right? So as in the Friday night hangout example, everyone knows when to start, end, or join a conversation. If two people started speaking at the same time, one person stops and lets the other person carry on until they are finished, then they share and vice versa. Another good um, analogy is when two people walk and bump into each other. So if they try to move in opposite directions but seem to still bump into each other, they consciously or subconsciously pick a time to wait. So imagine if you're like you're taking a walk and then you bump into someone else, right? You would like If you try to move the opposite direction and the person also does the same thing, and the both of you just keep going back to back to back, at some point you decide to just pick, like, maybe say 2 seconds to wait for the other person to pass. If the other person passes or doesn't pass after 2 seconds, then you would move, right? Um, so that is exactly how the contention-based network access system works or model works, right? I explained it here. Okay. Now, as you can imagine, the problem with using a contention-based method is that collisions can occur, right? And contention-based models can become extremely chaotic for networks. Oddly enough, the Ethernet is a contention-based networking protocol. But why? Why is that the case? You may be wondering. Why did they choose a contention-based network over a deterministic one? And the reason for that is because contention-based networks have much lower overhead, okay? Because you don't need to pass around that electronic token, that token that, going back to the classroom example that says it's now your turn to speak. You don't need to pass that in a contention-based network access model. And they can make better use of all the bandwidth of the network because anybody can talk at any time. So I'm just using that analogy of people, speaking in a classroom to make you understand what a contention-based network access model is like. So I know this might seem odd, right? But this is exactly rather this is actually a really good thing because compared to contention-based models, deterministic models waste a lot of resources. Therefore, Ethernet through its contention-based network access model significantly optimize the efficiency of network communication, right? Now we are going to go into a different topic, which is CSMACD or carrier sense multiple access with collision detection. I know it's a mouthful, but you understand what it is as we go on. So, how does Ethernet, a contention-based model, prevent network collisions? Ethernet prevents network collisions through a method known as CSMACD, carrier sense multiple access with collision detections, right? And we're going to understand what it is using this image. Okay, so just imagine by the way, these are different devices connected to one network cable. You could say this is just one Ethernet network cable. So this is known as one connection segment because it's one cable that's running all the way to all these different devices, right? And there are 6 devices here. So imagine that device 5 wanted to talk to device 3, or device 3 wants to talk to device 1, and device 5 at the same time also wants to talk to device 6. So now they are sending data, but because they're in one network segment, there is a collision domain. This is a collision domain because these two data are colliding, right? So there's a collision here. Now, how does Ethernet, like I said, how does it solve this problem? How does it prevent these network collisions? It does that through something known as CSMACD. Okay. Now, how does that work, right? So as seen in the image above, and as demonstrated in the analogy of two people walking by and bumping into each other, if two devices, device 3 and 5, want to transmit data at the same time in an Ethernet network connection, a collision occurs as marked by the red X in the diagram above here. Okay, so what then happens after that? Remember, like I said, if this was you, you would then say, okay, you just pick a random time. You would pick like maybe 2 seconds to wait for the other person to pass. If nothing happens, if the awkwardness remains, then you continue waiting. Otherwise, if the awkwardness is no longer there, you just move, you just pass, right? So the two devices pick a random time, or a random wait time. It's called a random back off time. So this device, which is device 3, picked 30 milliseconds back off time. Device 5 picked 150 milliseconds back off time. And I explained this here too, I believe. So let me just read through this really quickly just so that you understand. When a collision occurs, the two devices will choose a wait time, also known as a back-off time, at random, as seen in the image above. When the least wait time has elapsed, the device with the least wait time will restart its data transmissions again, as seen in the image below, this way preventing network collision as seen here. So by the time that device 3 waits for 30 milliseconds, nothing is happening. He then goes on to transmit his own data. Remember, at this time, device 5 is still waiting for 120 milliseconds, right? Now, this seems like a bad way of doing things, right? Because as our networks get busier and busier, and by bad way of doing things, I mean, just imagine that you had like 6 more devices, so 12 devices here now, and each single device had to wait for, every single device is speaking their own back off time. Before you know it, the bandwidth of the network would become so huge, and basically no one will be able to communicate, right? This is what I mean. So this seems like a bad idea because, like I said, our networks get busier and busier with more and more clients or devices, and we'll end up with more collisions. And you will be correct if you thought that. And that's why the more devices connecting a single network segment, the more collision will occur, right? Now, you understand what collisions are now, right? That means we can move on to the next topic, which is about collision domains, right? Now, each area of the network that shares a single segment. Remember, I said this is a segment, right? These networks are sharing a single segment. Each area of the network that shares a single segment is known as a collision domain. Okay. For example, all six devices are in the images above, as we've just seen, share one collision domain. Therefore, with Ethernet, anytime we have devices connected on the same cable or net or connected to a hub, we're going to learn about hubs later on down the line. Each time we have that happen, they are all going to be sharing the same collision domain. So if we have a very large collision domain, there's a very high possibility that collisions are going to occur, and each time a collision occurs, this requires the data to be retransmitted after waiting for a random backup timer to finish. And this slows down the entire network segment, and actually slows down the entire network to a much lower bandwidth than should be expected as well. So for this reason, we need to keep our collision domains small inside our networks, right? But how do we do that though? How do we keep our collision domains small inside our networks? We do that by using Ethernet switches or bridges. Okay. Now, Ethernet switching, which I hope you're not the whole idea of Ethernet switching, the concept behind it is now beginning to make sense. It's beginning to click. That was the reason why we had to go through the entire background to get here. Ethernet switching increases the scalability of a network by creating multiple collision domains. Note this: creating multiple collision domains. And that is a really good thing because when you look at a switch, such as the one below, this is a switch, by the way. I'm sure you'd have seen devices like this with Ethernet cables plugged into them, right? This is a switch. So Ethernet switching increases the scalability of a network by creating multiple collision domains, and this is a really good thing because when you look at a switch such as the one below, every single switch port, each port like this one, is considered to be its own collision domain. We're going to understand what that means exactly, and this increases the speed, scalability, and security of networks. Okay, so now the next topic, network infrastructure devices. Okay, now we're going to learn about router, switch, bridge, and hub. Let me just click this image so you can see it better zoomed in. We're going to learn about what each and every one of these devices do because as a cloud engineer, you're going to be dealing with switches and routers. You may not necessarily be dealing with hubs and bridges because you'll understand why as we move on. So it's important to understand how these work. So if we recall, in class 1, we mentioned some of the network devices we are soon to learn about in this section, devices such as these that we've just listed. So what is a hub? A hub is a multi-port repeater, a layer 1 device that connects multiple network devices and workstations. Okay, it's a multi-port repeater. It's basically a repeater. It repeats data signals. It doesn't do anything else. It just repeats data signals. So there are three different types of hubs. There's a passive hub, an active hub, and a smart hub. Okay, a passive hub is a hub that simply just repeats signals with no amplification. All right, there's no amplification. It simply repeats signals. An active hub is a hub that repeats signals with amplification. So let me just give you an idea, although we kind of, okay, let me not talk too much because we'll still go into it. So in other words, an active hub boosts a signal to a longer distance. So take this visual aid below, for example. Now, this visual aid below, these lines, slashed lines, right, that you can see here, this is an Ethernet cable, right? So remember I said there were some topics that we skipped to get to this part, some topics like media and connectors, where we learn about copper cables and fiber optic cables. There are Ethernet cables known as Cat5 Ethernet cables. Those cables can only transmit data within a 100-meter distance. Anything beyond the 100-meter distance and the data will be lost. So I mean, at huge data centers, or say maybe you're working for a company, um, that has its own data center, its own server room, you would need to pass a Cat5 Ethernet cable longer than 100 meters. You definitely need to do that. So the only way to achieve that is, you can imagine in this case, is to use a hub. So a hub simply repeats the signal. But remember, if you're using a passive hub, say for instance, you this is like 100 meters, although it's 60 here, but say this is 100, and this is a passive hub. If this is a passive hub, the hub is not going to amplify the signal, which means if the cable is already 100 meters and then you add a hub at the end of the 100 meter data, sorry, let me slow down a bit, 'cause I feel like I'm rushing. If the cable if is 100 meters and you add a hub at the end of the 100-meter distance, the signal is not going to be repeated. It's not going to be amplified because it's a passive hub. Okay. It's the fact, if anything, the hub will add to the distance that the cable cannot transmit data. So the kind of hubs that they use in cases like this are active hubs, because what an active hub would do is that it would amplify the signal. So that's the reason why in this case now they are passing a Cat5 Ethernet cable, right? 60 meters for each length in a pentagonal shape or pentagonal structure. So now this is an active hub. So when the signal is passed from say for instance from this hub to this hub, it's amplified 60 more meters. It now goes from this hub to this hub, it's amplified again 60 more meters, and it's able to go all the way around. So that's what an active hub does, and I explained that here as well. Now, a smart hub is an active hub with enhanced features like simple network management protocol, or SNMP, which we learned about last weekend, which allows you to remotely configure the device, right? So remember what we learned about collision domains, right? Ethernet switching, collision domains is very, very it's very, very fundamental to the concept of Ethernet switching. So it's important that you keep this word at the fore of your mind while we go through this. So remember, we learned about collision domains because, or rather, remember what we learned about collision domains because when we use a hub to connect multiple network devices together, what happens? What happens is that, just as you can imagine, in this case, right, we have this is one big collision domain because this is a hub. When we use a hub to connect multiple devices together with, Cat5 Ethernet cables, we are creating one big collision domain. So if this computer, let's call this computer, let's call this PC1. If this PC1 wants to communicate with this PC all the way here to the end, PC5, let's call it maybe PC4, then if at the same time this PC also wants to communicate, there's a collision between these two PCs, and then they now have to do the whole CSMA CD thing, contention based, right? They have to pick a back off timer and then wait for this other person to transmit data for the other person transmits data, that kind of thing. That's how it works. That's how it works, right? But this is, like I said, this is one big collision domain. So to reduce the potential network collisions, we need to break up the big collision domain into smaller collision domains. Can we do that with hubs? We can't do that with hubs. Hubs cannot do that. Okay. Why? Because hubs don't break up collision domains. Remember, hubs are pretty simple. All they do is just repeat signals. So hubs cannot break up collision domains. Instead, hubs connect them. So hubs connect collision domains together as you can see here. Something else to note as well within these images is also the symbols next to them, or the way that they are drawn. For instance, you can see a switch is two lines, like two arrows on each direction. Router is sort of cross lines on each direction, I guess, and bridge and then hub. Okay, so now we've talked about a bridge, right? And now we've said that can we use a hub to break up collision domains? We can't, because hubs only connect them, but we can actually use a bridge. And now this is why we need bridges, and this is why bridges were created. Remember, necessity is the mother of all invention. So when that issue was now became apparent, a bridge was then created. So what is a bridge? A bridge analyzes source MAC addresses and makes intelligent forwarding decisions based on the destination MAC address in the frames. Too many bulky words. What does that actually mean, right? A bridge will analyze the source MAC address. Remember, MAC addresses function at layer 2 of the OSI model. As we are going through this, you begin to understand a lot more how the OSI model functions and why it is even existent and how it works, right? And how data flows through one layer to the other. So a bridge analyzes the source MAC address. MAC addresses are layer two sort of concepts, because a MAC address is okay. You know what? As we go through this, I would it would be a lot more explained, so that we can have time to go through the rest of the things that we have for today. So in other words, a bridge will analyze the source MAC address in the frame and then populate an internal MAC address table. All right. Now, it does this through something known as app. This is not ACK. I know we talked about SYNAC before, but that's totally different. SYNAC is a three-way handshake that happens in TCP connections. This is not SYNAC. This is app. Okay. This is something totally different entirely. So, I'll just read it again. A bridge will analyze the source MAC address in the frame and then populate an internal MAC address through something known as app, which we'll talk about later. And then based on that table, a bridge makes forwarding decisions to the destination MAC addresses in the frames. Okay. I hope that makes sense, but we're going to understand more about it here. So a bridge is a layer 2 device, as you may have guessed. Remember, a hub is a layer 1 device, a bridge is a layer 2 device. Now, remember, this is the same image as the one we had here, right? But the connectors were hubs. There was no bridge here. Now, in this case, we have a bridge, and this bridge, as you can see, is dividing this domain and this domain. Now, it's dividing the collision domains. As it's doing that, it's breaking down the collision domain into a big collision domain. From a big collision domain into smaller collision domains, because as you can see now, the number of devices connected to this hub are now smaller. Before, it was like this hub was connected to device 1, 2, 3, to 3 more devices. Now it's only connected to just 3 devices. This hub is also only connected to only 2 devices now, and now there's a bridge in between them to break up the collision domain that would have otherwise happened between them. Now, something to note within this diagram too, we haven't yet talked about, but we will talk about, is a broadcast domain. Now, this entire connection domain system is referred to as a broadcast domain, but it's sort of use the word bridged, is bridged or divided by by a bridge, and what is divided by the bridge are the collision domains. Okay, it's important to know that. I go on to explain everything I just said there here, but let me try and see if I'm not missing anything. So as seen in the image above, that one big collision domain has now been broken up into 2 smaller collision domains. The bridge will only allow data to go across it when it needs to, based on its MAC address. Okay, let me explain this, but I'll be brief with this. So say for instance, this PC1 now, in this case, remember before it could simply just send the data from here to here. Obviously, for it to send data, it needs to know the MAC address. There needs to first of all be a connection to start with. That connection is made using TCP. Remember, using the SYNAC and ACK three-way handshake method. Now, while that connection is being made, it's going to send out a data packet to find the MAC address of the destination PC or the destination server it wants to communicate with which is going to make that connection, right? In this case, it would simply just send that data packet, but then it could be halted on its way by a collision, because another PC also wants to send its own data as well. So now, fast forward to this case where we now have a bridge demarcating into collision domains. If PC1 wants to send a message to PC2, what it's going to do is that PC1 will send that data packet to this hub. This hub is going to say, okay, wait, I don't know any PC that has this MAC address because it's not within my own collision domain. So what I'm going to do is that I'm going to send it to the bridge, because I know that there's a bridge connected to me. So I'll send it to that bridge, and I'll check if that bridge knows, if that bridge knows any PC that it may also be connected to, if it knows any PC that has this MAC address. So that data packet is going to leave this PC, come to this hub. Now this hub is going to send that data packet to the bridge. The bridge would then send that data packet. Sorry guys, I talk fast. I know. I'm trying to not talk so fast, but at the same time, I also know that we are kind of sort of low on time, so I'm trying to speak faster so that I can we can cover as much as possible before our time runs out. So when the data packet leaves PC1, goes into the hub, comes to the bridge will then send that data packet to this hub, and this hub will now be like, okay, wait, I think I have a PC that has this MAC address, and it's actually PC5 here. Now this hub will send that information back to bridge. The bridge will send that information back to this hub. The hub will send the information back to the PC. The PC will now be like, oh, thank you so much for telling me where this PC actually exists or where this PC is. Now I'm going to send the data I wanted to send to it. It will then send the data and it will go from the hub to the bridge to the hub again and back to the computer. But now the idea is that you can see it has reduced the collision domain that would have existed if not for the bridge. That is what bridges do. Okay. Everything I said there is explained here. Now, if we merge a bridge and a hub together in function, we get a switch. Okay. Sorry, let me just drink water. All right. So if we merge a hub and a bridge together in function, we get a switch. So you can already understand what a switch is and what it does. Now, a switch is a multi-port bridge, right? Multi-port. If you go back to that image of a switch, let's find it again. Right, multi-ports. It has multiple ports. It's a multi-port bridge. Okay, a switch is a multi-port bridge, a layer 2 device that connects multiple network segments together. With a switch, every single port acts as a hub with a bridge on every port. This way, a switch breaks up the collision domain into a single collision domain for each and every port. Switches make forwarding decisions just like a bridge does, based on destination MAC addresses. To reiterate, with switches, each port represents an individual collision domain, but every port on the switch is part of the same. Now we see this word being used. Every port on the switch is part of the same broadcast domain. Okay, what does that mean? This is what it means. Now imagine that same system that we had, right? Let me just go back. Here we had like 4 PCs and one server connected with hubs and a bridge, with 2 hubs and a bridge. Now in this case, we've deprecated the hub and the bridge because the switch is the 2 of them in one. So now we're using a switch, and now via a switch, we've connected. Remember, this switch, if you go back to that image of a switch has ports, right? Remember, we said a switch is a multi-port bridge. So imagine every single port has an Ethernet cable that's plugged into, that's plugged into one port and also plugged into a PC, into these PCs and a server. Now, each Ethernet cable that is plugged into each PC is its own collision domain. As you can see, this arrow here is showing this cable that runs from this server to this switch here is a collision domain on its own. Now, the fantastic thing is, as you can imagine here, we've broken the collision domain into 4 places now. Now there are 4 collision domains here. There's 1, 2, 3, 4. And there is only one device connected on that collision domain. What does that mean? It means the chances of a collision is really low because the only device here in this let's take this collision domain for example. The only device here that's going to send data through these segments, through its network segments, is only this server. There is no other computer or device or service connected to this same collision domain. Okay, so that means that because it's only the server, the chances of a network collision is very, very low. And that is what a switch, that is the problem that a switch solves, right? But with a switch, remember here it said, but every port on the switch is part of the same broadcast domain. That means that with a switch, all the devices connected to its port is one big broadcast domain. What does that mean? It means that this computer can communicate with this computer because it's within the same broadcast domain. This computer does not have to leave this local area network to communicate with this other computer. All it needs to do is send the data packets to this switch, which will then send the data packets to the computer that it needs to speak to because they all are in one broadcast domain, right? I hope that makes sense. Now, all this while, this is not supposed to be wave. I think this is supposed to be we are reminded. Oh, sorry. All this while we've remained. This is actually correct. I thought this was a typo. All this while we've remained in the local area network of the LAN, which is actually what this is. So now you can understand a lot more what LANs are. The connections and communications we've made have been within the network. When we want to go beyond the local area network to the internet, a switch cannot do that for us. We do that only using a router, and that is now where the router comes in. A router allows the devices that are connected within rather, the devices that are connected to a switch. A router allows those devices to then access the internet. So if any one of these computers wanted to access the internet to check email, for instance, or to check or to open a website, then it means that they will have to go beyond this switch. For them to do that, they need to be connected to a router. Therefore, this switch needs to be connected to a router. Okay. So, enter router. A router is a layer 3 device that connects multiple networks and makes forwarding decisions based on logical network information. Logical network information here just means based on things like IP addresses, MAC addresses, and so on and so forth like that. In other words, if we want to connect two dissimilar networks, like an internal network and an external network together, i.e., your LAN and the internet, then we need to make routing decisions, also known as forwarding decisions. And these routing decisions are made based on logical network information, such as IPv4 and IPv6. Right now, we're beginning to go into IP addressing. So you see the reason why I have to talk about Ethernet switching first, because that matters to really understand IP addressing. So two important things to note here. Switches are all about layer 2 and MAC addresses. Switches are all about layer 2 and MAC addresses. Remember, we've dropped hubs and bridges now because they're no longer relevant to us, because a switch is a hub and a bridge combined. Okay. Now, what we now deal with are switches and routers. And a switch is all about layer 2 and MAC addresses, while routers are all about layer 3 and IP addresses. One distinct difference between routers and switches is that routers separate broadcast domains, as you can see here. So we had something that separated collision domains, and first of all, it was a bridge. Then it was now a switch. But that switch had one broadcast domain. A switch, all the ports in a switch all comprise of one broadcast domain. But a router separates broadcast domains from each other, as this image is showing. This is a switch. This is one broadcast domain, and also each computer is its own collision domain, which means if it's only one device, I'll just explain this again. If it's only one device, it means the chances of a network collision is very low, because there's not going to be any other device communicating on that same network segment. So that's the switch, right? But now these are all collision domains, but this is one huge broadcast domain, right? And this router is separating these two broadcast domains from each other, right? Something else to take note of is a layer 3 switch. Now, a layer 3 switch is a switch or a router that's merged in function into one singular device. So someone had the idea of, okay, since we already merged the hub and a bridge together and we created a switch, why don't we just merge a switch and a router together and then create a layer and then create some device? So they did that, and they call that a layer 3 switch. So it can be quite confusing. But normally, if anyone wants to specify a switch that's able to access the internet, they will normally say a layer 3 switch, because normally a switch on its own cannot access the internet, because it would need a router to do that. But a layer 3 switch is a switch and a router merged in function together. So this is often used today in the real world in place of a single or a simple switch. Although layer 3 switches, majorly perform the task of a router, but network technicians usually advise that in larger network connections, routers and switches should be used instead of layer 3 switches. Okay, so I don't know how much I don't think I can assure you, to be fair, but I would guess that in AWS and other huge cloud platform data centers, even though they may use layer 3 switches, they most likely use just switches, because switches work better. Switches and routers, that is, because they both work better, for data centers. So that's all about Ethernet switching with regards to network infrastructure devices, and understanding how Ethernet network, like how the Ethernet moves network, how data flows from one network segment to the other, or rather from one device to the other via the Ethernet cable. And we talked about the deterministic system or model, and then the contention-based model. And we said that Ethernets work with the contention-based model. Now, speaking about VLANs, what's a VLAN? A VLAN is a virtual local area network. A VLAN is a logical subdivision of a given network that segments into separate broadcast domains. Okay, so basically a VLAN is a subdivision of the physical LAN that you see, but it's a software feature, so it's a subdivision within sort of a software environment, you could say. So you can sort of read up on all of that on here. I don't think I need to go into that just because of time, because we're really losing time and we have so much more to talk about. So the only thing I think is important to note here is that before VLANs were used, just to understand why VLANs are available today, network administrators had to install additional routers, cables, switches to all these things, all these devices to separate out each of the different network segments. Like say for instance now, if in a particular company, the company wanted to have an HR department sort of space or HR department network and an IT department network and so on and so forth like that. Before, back in the day, network administrators or technicians would have to install physical devices like switches, routers, cables, all those things to make that work and to make that possible, to make that happen. But today, due to VLANs, because VLANs are mostly software, I think I explained it here, right? Since they are software configurations, all the network technician needs to do is just to set it up virtually, so that these different departments can be divided. So that's all about VLANs. There's really not much else um, depth. I mean, you can't actually go into much depth in there, but we're not going to talk about that today. So the next is network access control, NAC. So NAC is a method for increasing the security of a given network by inspecting devices trying to connect to a network. So when you think of NAC, right, think of the customs inspection checkpoints at international airports when you're about to travel. When you go up to the counter, the immigration official checks your particulars to certify if you are allowed to access the country. If you pass the check, you'll be let into the country. But if you fail the check, you'll be put in a special holding area, sort of like a quarantine area, for additional screening and remediation. So with NAC, each device presents itself for inspection when it first attempts to connect to the network. So think of NAC like when you're trying to log into something. For instance, when you're trying to log into AWS, right? And then you have to put in your password. That's a network access control. So NAC inspection checks include port security, MAC filtering, 802.1x authentication, or Wi-Fi authentication. Remember I said anyway you see 802.11 or 802.1, 1x, 1q, and I think 1d2 and so on and so forth like that. Anyway, it's Wi-Fi related. 802.1 is a code name for Wi-Fi in the networking world. So yeah, anyway, see 802.1, it's Wi-Fi related. So NAC inspection checks include things like port security, MAC filtering, 802.1 authentication, and Wi-Fi authentication like passwords and so on, captive portals and so on and so forth like that. Now NAC can be tailored for specific requirements also, such as time-based security, location-based security, role-based security, and rule-based access control. All right. Now we're just going to learn a bit about what these things are. Time-based access control in NAC is used to limit a device's network access to specific hours based on the organization's operational schedule. So a time-based access control will be something like say you were working in this company that say this company worked like 9 to 5, for instance, right? Um, this might even be a really really good example. Say we're working remotely for a company that only allowed you to access your AWS account from say 2 a.m. in the morning to 6 a.m. in the morning. Maybe you're working for this overseas American company that only allowed you to access your AWS account from 2 a.m. in the morning to 6 a.m. in the morning. If you try to access that account from 2 p.m., you wouldn't work. You won't be able to access that account because it's blocked. Why? Because it's a time-based access control. That's basically what time-based access control is. Location-based access control, as you can imagine from the name, it's location-based. So if you're working for, say, maybe a regional company, maybe like a medical company, for instance, and the CEO says something like, I want you to set up a network system for me where my staff can only work with our devices and with our users' data, maybe based on security. They can only work on those on like all that user data while they are while they are in the premises of the business, while they are like in the location. So say the company is in Lagos, in Kaduna, in Owerri, in these places. Um, when you set that up using a location-based access control, if someone wants to access that company's user data from, say, Nasarawa, it won't work because it's location-based. So you can imagine the same goes for role-based, rule-based. Role-based, you kind of already know that already. This NAC method is used in AWS Identity Access Management, or IAM, to determine user or service access to specific services using roles. That's role-based access control. Rule-based access control is in NAC operates on a set of sorry in NAC operates on a set of predefined rules or policies. So to methodically grant or deny access by assessing logical conditions and statements based on the specific user's identity and context. So what this all means is that this NAC method is used in AWS IAM to determine user or service access to specific services using groups and policies. So groups and policies are a really good example of rule-based access control, where there are a set of predefined rules or policies that allow a user, or that allows the network to methodically grant or deny access to a particular user that's trying to access the network. Imagine it's already 5:30 and we've not even talked about IP addressing. This is where we are. This is how much more we have to cover. Wow. Okay. So, what do you guys think? Let me go back to the chat. What do you guys think? Do you think that we should end this now, and maybe pick up from here next time, or do you think that we should go and maybe give it like 15 more minutes? What do you think?
I think we should do 15 more minutes.
15 more minutes. All right. Cool. Okay, 15 more minutes, right? So I will try and speed through this. So maximum transmission unit, or MTU. Now, MTU refers to the largest size of a data packet or frame, right? That can be sent over a network. The largest size of a data packet or frame, sorry, the largest size of a data packet or frame that can be sent over a network. Now, a frame size is measured in bytes, right? And the frame size dictates how much data can be sent and processed by a network in a single transaction or transmission. In other words, an MTU is a maximum load capacity, or rather, the maximum load capacity of frames within a network. So to understand this in like, to sort of bring it down, make the understanding a whole lot more elaborate for you. A good analogy for MTU in a how did I say? Okay. So I said a good analogy for MTU in a network is an elevator in a high-rise building. So the elevator would have like a maximum capacity, right? Something like 10 people, or 2,500 pounds. In the same way, that's basically what an MTU is for a network. So an MTU is like the maximum capacity for an elevator. So MTUs impact the performance and efficiency of a network, right? A properly configured MTU ensures that the data packets or frames are neither too high or too small. If it's too high, there is packet loss. If it's too small, there is increased overhead. Now, I want to show you this. When you go on, when you open, when you go on your Linux command line, just to show you that these things we're actually talking about here, these things matter, and they help you to further understand further understand computer networks, and then how to tweak them and make them, use them to achieve, you know, the things that you want to achieve. Um, when you type within your command line IP address show, it shows you all these things, right? So we're going to talk about what loopback is. We're going to talk about that as we talk about types of IP addresses. But also, it also shows you this ETH0. This ETH0 is Ethernet 0, which is the first Ethernet cable that's connected. Remember, we talked about collision domains. So just imagine that this is like a port, right? And we'll talk about we've actually already talked about broadcast, right? Broadcast domain. So this is telling you that this is connected to, so every device that's connected to this subnet mask here, which we're going to learn about as time goes on, is all part of the same broadcast domain. And broadcast is enabled here. Multicast, we're going to learn about multicast. Up means that it's available, it's working. Now, the part that I want you to note here is MTU 1500. This tells you that the maximum transmission size for a wired Ethernet network is 1500 or 1500 bytes, and that's what we can see here. Okay, let me just scoot through that. Now that is usually the usual frame. Like, remember, a properly configured MTU ensures that the data packets of frames are neither too high or too small. So MTUs are the maximum capacity of data packets of frames that you can transmit over a network. Okay, and the usual amount for a wired Ethernet network is 1,500 bytes. Now there are such things as jumbo frames, frames that are too big, frames like that are really big. You know, usually have a default size of 9,000 bytes. So these larger 9,000 byte frames are beneficial when working in storage area networks because they enhance the efficiency of data transfers by reducing overhead. So jumbo frames like this are usually used, they're usually ideal for high bandwidth applications such as storage area networks, large file transfers, video streaming. Like as we are streaming right now, we are using a jumbo frame to transmit this data, over our network, right? The MTU size for this stream that we're having right now is a jumbo frame, and that size is 9,000 bytes. So we have a quiz here. I do not know if okay. Let's go through this quiz really really quickly. Wherever we stop here, we'll continue again when we have our next class. Okay. So question number one. This is just again to rate, to sort of gauge if you've been listening to me and to gauge if you've been learning as well. Okay. So question number one: in a corporate network, unauthorized devices connecting to Ethernet ports pose a security risk. What feature can be implemented to restrict access based on their allowed MAC addresses? Which one of these do you think is the right answer? VLANs, port security, DHCP snooping, SCP, spanning tree protocol. Which one of these do you think is the answer? Let me actually check the chat because I can't actually see it myself from here. Okay, there hasn't been any message in the chat.
I think it should be B.
B. Okay, so let's see if the answer is B. So you can find that out, but when you click this C answer, and when we do that, right, the answer is B. It's port security. And when you read through this, it explains the reason why port security is the answer. But we discussed that it's designed to restrict access to the network by filtering MAC addresses, which is the answer to that question, right? But yeah, on your own, when you go through this notion board, you can discover the answers from there. Where were we now? We've gone way down now. Okay, right. So question number two, which network devices function at layer 3 of the OSI model? Is it the hub and a bridge and layer 3 switch, a switch and a hub, or a layer 3 switch and a router?
I think the answer is D.
Right, fantastic. Thank you very much. The answer is D. And like I said, yeah, that's it. The answer is D. And when you go to, when you click on this C answer, you would see, that the answer is D, and then you will see the explanations to why that's the case as well. Thanks for that. So we go on now to talking about IP addressing. Oh my God, we've spent an hour talking about Ethernet switching, but I hope it's been valuable and it's been useful, and you've learned something from that. So now we're gonna now start delving deeper into IP addressing. So what is an IP address? An IP address is an assigned numerical label that is used to identify internet communicating devices on a computer network. It's an assigned numerical label that is used to identify internet communicating devices on a computer network. IP addresses are used at layer 3 of the OSI model. So remember, layer 3 of the OSI model is the network layer, right? So that's where IP addresses are used, and they're used by routers to send data from one network to another. And this tells you that routers are a layer 3 device, as the person that answered the last time rightly said. A router is a layer 3 device. We kind of just, I just touched up on it here. So to understand the concept of IP addresses, your IP address is to your computer what your mailing address is to your house or your office. And I think you understand this. Now, their IP addresses come in two formats: IPv4 and IPv6. IPv4 addressing, right, is our next topic. And focusing on IPv4, we are focused. I mean, even though we'll talk about IPv6, but the focus will really be on IPv4 because it's popular and it's the most common type of IP addressing that is used in our networks today. So examples of an IPv4 address is something like this, 10.1.2.3 or something like this. It can get really complicated like this, 172.21.243.67. So as seen in the example addresses, an IPv4 address is made up of 4 decimal numbers separated by a dot. For this reason, this format is called a dotted decimal notation. Dotted decimal. Okay. When we are referring to each of the 4 decimal numbers individually, when we are referring to each one like this, each one individually, we call it an octet. Okay. Now each octet is the size of 8 bits. All these things are very important to note, but again, I'm going to share this notion board to everyone so you have access to it. So since each octet uses a decimal number to represent an 8-bit number, each octet can be represented by values from 0 to 255, which is a total of 256 decimal number values. Okay, so this is a visual aid to understand everything that I just said. So therefore, when we summarize that an IPv4 address is represented by 4 octets, each containing 8 bits, resulting in a total of 32 bits for the entire addressable space. Okay. Now, the way computers read IPv4 addresses is in binary digits, not in decimal digits. So computers don't understand decimal digits like this. Computers understand binary digits like this. So like this. Okay. So these decimal digits are converted to binary digits for the computers to read them and understand them. But for us, to help the human eye, we convert them to decimal digits and we represent them in decimal digits so that we can, communicate better and understand what we are actually telling computers to do. So this is just another sort of signification of it here. So each IPv4 address is created using 2 portions: the network portion and the host portion. Okay. So when we look at an IP address like 192.168.1.4, it's actually broken down into 2 portions. Okay. So the 2 portions is broken down into is the network portion and the host portion. Don't forget about that; it's important. The network portion and the host portion. So by using a second 32-bit number known as a subnet mask. So what this means is that the network portion and the host portion is signified by another or a second 32-bit number known as a subnet mask. Now we are introducing a subnet mask. Now in this case, you can see this is 192.168.1.4. This is the binary digit that represents this decimal number. Now the network portion and the host portion of this IP address 192.168.1.4 is signified by this subnet mask 255.255.255.0. It can be easy to confuse the subnet mask when it's in decimal form, as shown in the image below. So it can be easy for someone to confuse this as this, right? When it's in decimal form, as it is here. Okay. But if you look at it in binary form, you'd realize that there's continuous and consistent strings of zeros and ones. Okay, as you can see here, consistent strings of ones and zeros. The ones represent the network portions, and the zeros, the host portion. The zeros represent the host portion, and the ones represent the network portion, as seen here. So what this means is that 255.255.255 is the network portion, and this 0 here is the host portion. We're going to understand what network portion and host portion means and what it actually does, why, like what the value is, and so on like that. So if you see a 0 in the binary representation of the subnet mask, that's the host portion of the IPv4 address. Okay, and where you see this, this is a typo, and where you see a 1, that's the network portion of the IPv4 address. Again, as signified here, the concept of a host and a network portion would become more apparent when we learn about subnetting, because it plays a crucial role in subnetting. We are not going to learn about subnetting yet, because that's something that we're going to talk about in the future. Okay, in our next class. So putting this all together, our IPv4 address is this, our subnet mask is this, and this means that 192.168.1 is our network portion. Hence, anytime we see another IPv4 address that starts with 192.168.1 sharing the same subnet mask of 255.255.255.0, then that IPv4 address is addressable as part of the local network because it shares the same network portion as specified in the image below. So what that means is that anytime we see another IP address that is something like 192.168.1.50, for instance, that means that it's sharing the same network portion. In other words, it's in the same LAN. They are sharing the same switch. Okay. But this will make a lot more sense as we learn, as we go further on, and as we learn. Now, anywhere I see zeros in it, okay, yeah, this just explains everything that we said. But this is the point that I want you to get here. Actually, let me read this again. Now, anywhere I see zeros in a subnet mask that represents the host portion, that represents the host portion of the IPv4 address. In this case, that's the point 4. This point 4 here. That's the point 4 portion of the address of 192.168.1.4. That point 4 represents a specific host. For instance, you can have a server, a desktop, a laptop, a tablet, a printer, or any other network device that is assignable or assigned to that IPv4 address. So this is a very good example. So you see this now. This IPv4 address and this IPv4 address are in the same network portion. In other words, they are in the same, you could say, subnet. You could actually say that they are in the same subnet, but I don't want to confuse you with subnets now because we haven't started learning about that. But they basically are within the same local layer network because their subnet mask is 255.255.255.0, and you will understand why that's the case. I don't think we'll have the time to talk about it in this class, perhaps in the next one. But I would end. I don't even think we have time to talk about classes, right? So this is where I'll end. I'll end here. I think I'll end here. Okay. So what did we just talk about? Let's see. We talked about the network portions and host portions of IPv4 addresses, right? And and right, and then right here. And then we talked about how that if any other IPv4 address has 192.168.1. say 50 and they both share the same subnet mask, then we know and understand that those two IP addresses are within the same network portion, which means that they are within the same local area network. So that's what I explained here. I said, so if I have an address like 192.168.1.50 and another address like 192.168.1.4, both sharing the same subnet mask of 255.255.255.0, they will communicate using a switch, and they wouldn't have to use a router to communicate. Why? Because they share the same network. So this is where we're going to end today. Thank you so much for attending. Thank you so much for allowing us to push this further for another 15 minutes. When we have the next class, which may also be next weekend as well, we're going to go deeper to talk about a lot more because we still have a lot more to talk about. We're going to talk about IPv4 address classes, the characteristics of IPv4 address classes, subnetting in brief, and then what they call classless inter-domain routing. I hoped we would actually talk about that in today's class because on AWS, you would have seen something like CIDR notation or CIDR. You would have definitely seen something like this. So I wanted to explain this to you so that you understand it when you're actually using it in AWS. And then we also want to talk about IPv4 address types, public, basically types of IPv4 addresses. Public addresses, private addresses, loopback addresses, what they call APIPA or APIPA, and then IPv4 data flows, assigning IPv4 addresses, computer mathematics, and then subnetting in a whole lot more detail. So this is where we're going to end today. Thank you so much again for attending. And
Thank you for hosting.
no worries, bro. No worries. Let me stop sharing my screen here. Or actually, let me stop the recording.